All right, let's dive into one of the most incredible high stakes races happening in technology right now. We're talking about the global push to build a truly powerful quantum computer. And you know what? In this race, the finish line itself has just changed. So the big question is, who's going to win? I mean, who is going to be the first to build the machine that could literally change everything? This isn't just a simple competition. You've got global tech giants going head to head with these brilliant, scrappy startups. And every single one is betting on a completely different way to get to the finish line. You see, as of 2026, we are officially in a new era of quantum computing. For the longest time, the name of the game was just more qubits. Just cram as many of these quantum bits into a machine as you possibly could. Now, a qubit is the basic building block, right? But unlike a regular computer bit that's a simple 0 or 1, a qubit can be both at the same time. That's where all the magic comes from, but it also makes them incredibly fragile and unstable. So the race has shifted. It's not about quantity anymore, it's about quality. The new goal is building better, more stable qubits that actually work reliably. And this is the new finish line, the fault-tolerant quantum computer, or FTQC. This isn't just a slightly better computer, it's the holy grail. An FTQC is a machine so powerful it can actually correct its own errors, which, by the way, is the single biggest problem in quantum computing. We're talking about a machine that could solve problems we currently think are impossible, like designing brand new medicines molecule by molecule or creating truly unbreakable codes. This is the ultimate prize. So who are the main players in this incredible race? Well, it's not just a one-on-one. We are looking at a full-on five-way battle with five totally different approaches to building one of these machines. Each has its own playbook, its own strengths, and its own weaknesses. Okay, so here's the whole field of play laid out. Let's do a quick rundown. First, you've got the superconducting approach, backed by giants like IBM and Google. Think of them as the speed demons. They're incredibly fast. The catch? They have to be kept colder than deep space to work. Then you have ion trap. These are the precision artists, super accurate, but a bit slower. The new kid on the block is neutral atom, which is scaling up its qubit count like crazy. And finally, you have the marathon runners, the ones playing the long game. The silicon approach, hoping to use regular chip factories, and the photonic approach, which uses light itself and, get this, can work at room temperature. Every one of these is a different bet on what the future looks like. So let's focus in on the two that are really leading the pack right now. Their whole competition boils down to a classic tech dilemma. Is it better to be the fastest, or is it better to be the most accurate? So in one corner, you've got the superconducting teams with IBM and Google. Their entire strategy is built on speed, speed, speed. In the other corner, you have the ion trap method. Their priority, getting the answer right every single time, no matter what. It really is a battle of speed versus perfection. And that's the drama at the heart of the race today. And let me tell you, Team Speed has some serious momentum. Google, especially, hit a massive milestone with their Willow chip. They basically proved a core idea of what's called quantum error correction. The idea is, you take a bunch of those fragile, unreliable qubits, and you bundle them together to act as one super stable, logical qubit. And the huge breakthrough was that they showed that as they added more of the fragile qubits, the error rate of the logical one actually went down. This was a massive proof of concept. It was a huge deal. But don't count out the other frontrunner. While Team Speed was doing their thing, the ion trap camp, led by a company called Quantinuum, made huge waves. They came out and basically claimed to have built the world's most accurate quantum machine. They showed incredible results using those same error-corrected logical qubits. So if the superconducting method is the lightning-fast sprinter, the ion trap method is the master archer, who hits a perfect bullseye every single time. Just when you thought it was a simple two-horse race between speed and accuracy, everything changed. A dark horse suddenly surged forward and is now a real, genuine contender. And this number right here is exactly why. The neutral atom approach has just blown everyone else out of the water on one specific thing, the raw number of qubits. We're talking machines with over 1,000 of them. That incredible scale is why everyone in the field is suddenly paying very close attention. So how are they doing it? It's honestly amazing. They use these super focused laser beams that act like optical tweezers, basically tiny little tractor beams. They can literally pick up and arrange individual atoms one by one. This gives them incredible flexibility, and it makes building huge arrays of qubits way easier. And this isn't just a theory in a lab. They have large-scale test beds up and running right now. Okay, let's zoom out. We've seen the sprinters and the dark horse, who are all fighting for short-term wins. But there are two other contenders running a totally different race. They're not trying to win tomorrow. They are training for the million-qubit marathon. And that brings us to maybe the single most important word for the future of this race: scalability. Because to solve the truly world-changing problems, we're not going to need hundreds or even thousands of qubits. We're probably going to need millions of them. So the real question is, which one of these technologies can actually get us there? So these marathon runners are making two really clever bets. The first is the silicon approach. And the genius here is basically saying, why reinvent the wheel? Let's just use the multi-trillion-dollar industry we've already built to make computer chips. If they can pull it off, the scale could be enormous. The other long-game bet is the photonic approach, using particles of light. And its killer feature? It doesn't need to be frozen to near absolute zero. It can work at room temperature. Plus, since it uses light, it's basically designed from the ground up to network quantum computers together. So, we've met all 5 contenders. We've looked at their strategies. But all of this brings up a really fascinating question. What if we've been thinking about this whole race completely wrong? What if there isn't going to be one single winner? Because the biggest trend that's really taking over in 2026 is this simple idea: the future is hybrid. People are realizing this isn't a winner-take-all game. Instead, it looks like we're moving towards a future where all these different technologies work together. Quantum computers aren't going to be lonely geniuses. They're going to be team players. So what does that hybrid future actually look like? Well, it means using the right tool for the right job. Maybe for one part of a huge problem, you use a super-fast superconducting machine. And for another part, you use a hyper-accurate ion trap computer. And, this is crucial, it also means quantum computers will work hand-in-hand with the classical supercomputers we already have. That's the vision that companies like Fujitsu and NVIDIA are pushing for. Which leaves us with a final thought. We started this whole thing by asking who's going to win the race to build the ultimate computer. But maybe the ultimate computer isn't a single machine at all. Maybe the real winner is going to be a powerful new team, a hybrid of classical computers and multiple quantum technologies, all working together to solve our biggest challenges. What do you think?